Sampling methods in research, random, stratified, and more. How does one select a representative subset from a vast population to yield reliable research findings, and what roles do random, stratified, and other sampling techniques play in ensuring the validity of conclusions drawn from limited data? Research sampling is often initiated with the goal of achieving an unbiased representation of a population by employing methods designed to mimic the overall diversity within a manageable set. Traditional techniques such as random sampling, where every individual has an equal chance of selection, are grounded in the principles of probability theory and are intended to minimize selection bias. So far, so good, until we probe the nature and implications of these sampling methods more deeply. The sampling method's paradox emerges when the theoretically simple principles of random selection meet the practical complexities of real-world research. Under ideal conditions, a truly random sample would perfectly reflect the population. However, achieving true randomness is often hampered by logistical constraints and the heterogeneity of the target population. For example, while a random sampling process might seem to promise impartiality, subtle biases in the sampling frame or non-responses can significantly skew the results. It is much like casting a net into the ocean with the expectation of catching a variety of fish, only to find that certain species, perhaps deeper dwelling or more elusive, are underrepresented, thereby distorting the overall catch. Moving further into the landscape of sampling techniques, stratified sampling refines this approach by dividing the population into distinct subgroups or strata based on particular characteristics, then randomly selecting samples from each subgroup. This method is designed to capture the nuances of each segment, ensuring that the unique attributes of different subpopulations are not lost in the aggregate data. Consider an election poll that must account for various age groups, income levels, and geographical regions. Stratified sampling operates much like an artist selecting a precise palette of colors to accurately portray a landscape. Each color or stratum is carefully represented to ensure the final image is balanced and true to life. Beyond these, additional sampling methods such as systematic and cluster sampling further illustrate the diversity and adaptability required to navigate different research scenarios. In systematic sampling, individuals are selected from an ordered list at regular intervals, which can simplify the process while still maintaining a level of randomization, though it may inadvertently coincide with underlying periodic patterns in the data. Cluster sampling, on the other hand, involves grouping the population into clusters, often based on geographic or organizational boundaries, and then randomly selecting entire clusters for study. This approach can be likened to exploring a vast forest by randomly choosing specific groves rather than attempting an exhaustive survey of every individual tree, thereby achieving efficiency at the potential cost of increased sampling error if the clusters are not internally homogeneous. As with the transition to turbulence in fluid dynamics, where a modest perturbation can catalyze a cascade of unpredictable eddies, the choice and execution of sampling methods are profoundly influenced by external factors and inherent limitations. Environmental influences, the quality of the sampling frame, and the specific research context can all modify the expected outcome, so that even identical sampling techniques can yield divergent results under varying conditions. In practice, researchers often confront the challenge of reconciling the theoretical purity of a sampling method with the messy realities of fieldwork and data collection. The differences between methods, each with its own strengths and vulnerabilities, serve as a testament to the complexities underlying even the most seemingly straightforward aspects of scientific inquiry. The sampling method's paradox is not a failure of sampling theory, but a stark reminder that while the foundational principles of representative selection are well established, the practical application of these principles necessitates a nuanced understanding of the interplay between ideal models and real-world conditions. Just as in fluid dynamics, where tiny disturbances can completely alter the flow from laminar to turbulent, even minor imperfections in a sampling process can lead to significant deviations from expected outcomes. This complexity challenges researchers to continually refine their techniques and remain vigilant about the assumptions underlying their methods, an endeavor that is as much an art as it is a science in the quest to mirror the intricate tapestry of the real world in a manageable and informative sample. Sampling methods provide a systematic approach to selecting a subset of individuals or elements from a larger population for the purpose of making inferences about that population. These methods are critical because they affect the reliability and generalizability of research findings. By choosing an appropriate sampling design, researchers can minimize bias and improve the accuracy of conclusions drawn from the study. Example, a health study may select a representative group of participants to estimate the prevalence of a disease in a larger community. Analogy: it is like tasting a spoonful of soup to judge the flavor of the entire pot. If the sample is representative, the assessment will be accurate. Random sampling involves selecting individuals from a population in such a way that each member has an equal chance of being chosen. This method reduces selection bias and ensures that the sample is representative of the overall population. The randomness in selection also allows for the application of probability theory in analyzing the results. Example, a national survey may use random digit dialing to choose participants from a telephone directory. Analogy, it is like drawing names from a hat, ensuring that every name has an equal opportunity to be picked. Stratified sampling divides the population into distinct subgroups or strata based on specific characteristics before randomly sampling from each subgroup. This method ensures that key segments of the population are adequately represented in the sample. By maintaining proportional representation, stratified sampling can lead to more precise estimates compared to simple random sampling. Example, in a study examining income disparities, the population might be divided by age groups, with samples drawn randomly from each age group. Analogy, it is like slicing a cake into different flavors and then taking a piece from each slice to get a taste of every flavor. Cluster sampling involves dividing the population into clusters, such as geographic areas or institutions, and then randomly selecting entire clusters for the study. This method is particularly useful when the population is spread over a large area and a complete list of individuals is unavailable. The approach simplifies data collection while still aiming to maintain representativeness, though it may introduce higher sampling error compared to stratified methods. Example, a national education survey might randomly select schools from various regions and then survey every student within those schools. Analogy, it is like choosing a few entire neighborhoods to study community behavior rather than selecting individual houses scattered across the city. Systematic sampling involves selecting every kth element from an ordered list of the population after a random starting point. This method is straightforward to implement and can provide a sample that is evenly distributed over the population. Although systematic sampling is efficient, it may introduce bias if there is an underlying pattern in the ordered list that correlates with the selection interval. Example, in a quality control process, an inspector might check every 10th item produced on an assembly line. Analogy, it is like reading every 5th page in a book to get a sense of the overall content, assuming the pages are randomly representative. Convenience sampling selects individuals based on their easy accessibility and proximity to the researcher. This non-probability sampling method is often used when time or resources are limited, though it may not yield a representative sample. Because it does not use random selection, conclusions drawn from convenience samples must be made with caution due to potential bias. Example, a university study might survey students who are readily available in the campus cafeteria. Analogy, it is like tasting only the desserts on display in a bakery, which might not accurately reflect the quality of all the baked goods offered. Each sampling method carries inherent biases and limitations that can impact the validity of the research findings. Probability-based methods like random and stratified sampling minimize bias, but even these can be affected by issues such as nonresponse or measurement error. Non-probability methods, while cost-effective and convenient, often lead to questions of representativeness and external validity. Example, a phone survey may suffer from bias if certain segments of the population are less likely to have or answer a phone, thus skewing the results. Analogy: it is like trying to gauge public opinion by only surveying people in a single location, which may not reflect the broader community's views. Effective sampling is essential for ensuring that research findings are valid and generalizable to the broader population. A well-designed sample allows researchers to draw conclusions with quantified confidence and understand the extent of any error. Sampling decisions directly affect the credibility of a study and are a cornerstone of rigorous research methodology. Example: in public health research, a well-constructed sample can help accurately determine disease prevalence and inform policy decisions. Analogy: it is similar to building a puzzle. If you select representative pieces that fit together, you are more likely to see the complete picture accurately. The evolution of technology is expanding the toolkit for sampling methods, integrating digital platforms and big data analytics into traditional approaches. Emerging methods such as online surveys, mobile data collection, and algorithm-based sampling are changing the landscape by providing faster and often more diverse data sources. As these digital methods are refined, they offer promising avenues for enhancing representativeness and reducing bias in contemporary research. Example: social media platforms now enable researchers to reach targeted demographic groups rapidly, using data analytics to refine sampling strategies. Analogy: it is like upgrading from a paper map to a dynamic GPS system that continually adjusts based on real-time data, enhancing both accuracy and efficiency.